Now joining us, DARPA Microsystems Technology Office Director, Dr. Mark Rosker, and Deputy Director, Dr. Dev Palmer.
We will be talking to you over the next few minutes about working with DARPA and in particular working with MTO. We think of this as MTO 101. So we want to tell you about ourselves, what our mission is, how we work with some of the other offices, and ultimately we would like to describe in some detail some of the ways in which we encourage you to work with us and with our program managers. Most of this session, I believe, I hope, will be interactive, question and answer, but I'll start with a brief overview that gives you a flavor of some of the topics that I just discussed. So let me begin with DARPA. Many of you are very familiar with DARPA, but for anyone who is not, the history of DARPA invariably starts with Sputnik, because Sputnik is the moment in history that was the genesis of DARPA as an organization. As you know, Sputnik was a satellite launched by a foreign power, and that moment was a moment of technological surprise. The nation did not anticipate that was likely to happen. As a result, one of the many results of Sputnik, DARPA was established to guard against technological surprise, and that was and remains our mission today. Now, the way in which we are organized is in 6 different technical offices. They range on this chart from the Biological Technologies Office and the Defense Sciences Offices. These are more technology offices focused on early research. On the right-hand side of the slide, you see the Strategic Technology Office and the Tactical Technology Office, which are more about developing systems and platforms, so large implementations of technology. We live in the middle with our partners, the Information Innovation Office, which is more focused on software and cyber sciences. We are interested in hardware, and we're interested in a number of topics that we'll get to in a few minutes. So we depend on the technical offices, the technology offices for early foundational research, and we also depend on STO and TTO, the systems offices for transition. And that puts us in a position to be coupled to the entire organization. Very briefly, this is a second slide. This is a org chart which gives you some of the names of the office directors and deputy directors in the various offices, and a little bit more detail about some of the specific areas that each office is interested in. Now, the unique thing about DARPA, and the thing that really separates it from other organizations, is the way in which we do business. And specifically, the fact that we have chosen to have a structure in which the people, the program managers, and the directors have limited tenure. You come to DARPA for a brief period of time. You explore an area that you are particularly excited about, and then you leave and are replaced by someone else who has new ideas and different ideas. And this makes it a very dynamic organization. In terms of processes, all processes really have to be very fast by virtue of the fact that there's such large turnover in the organization. And from the standpoint of culture, that derives a very risk-tolerant view. So the kinds of programs and topics that we are interested in are generally quite exciting and hopefully lead to high payoff technologies when they work. It's probably worth a moment to say that because of the high turnover, we are always interested in looking for program managers. So if you are interested in public service and think you would be interested in joining us, please let us know. We're very much interested in that. So the acting director, Peter Heilmeier, uses this slide when he is describing the organization. Generally, lots of interesting numbers at the top, the number of program managers and the size of our budget and so forth. You find that there are actually very few program managers at DARPA. We're a very small organization. From the standpoint of the technologies we're interested, he groups them into 4 different areas: defending the homeland, deterring and prevailing against high-end adversaries, stabilization, and at the bottom, something called foundational research. Much of what MTO does can be found in the bottom area. You can see ERI called out as a specific example on this slide. But we have interest in MTO across the entire surface of this chart. And the one that I would call out in particular of interest is right in the center, control of the EW spectrum. All right. So having said that very briefly, let's get to MTO and let's talk for a moment about the Microsystems Technology Office. So it's always good to begin with our mission. What is MTO about? And this slide says very clearly that our mission is really associated with delivering the technologies that enable higher performance and intelligence in specific areas of interest, C4ISR, EW, and directed energy. And I'd like to say that the message at the very bottom of the screen is a really critical one. And that is that the reason why MTO exists, the reason why it was founded and why it's still here almost 30 years later, is because if you are interested in building systems like this for national defense, the availability, the effectiveness of these systems is largely dependent on the microsystems, the microelectronics, the photonics, the MEMS, the microsystems that are contained at the leading edge of these systems. So it's our job to ensure that we have an advantage over our adversaries in all of these areas. That's our goal. That's what we're trying to do in MTO. And the way in which we try and do it is through 4 thrusts. And we're going to talk a little bit about these thrusts over the next few minutes. So I'll explain them in more detail. But very, very briefly, what these are number one, localized processing, enabling microsystems to be more intelligent. And number 2, electromagnetic spectrum dominance. So the front-end technologies that allow systems to see better and to actuate better than existing than adversary systems. So those are component technologies. The third area is the integration of those component technologies into microsystems. And it's not just the integration themselves, but also their design and their security, which is part of that. And finally, the last area, which as we'll get to, is combining all of those elements, including the integration, into functional microsystems to deliver specific capabilities. So let's go through these one at a time. And some of these, as we'll see, are ERI topics, and some are non-ERI topics. So many of these themes will be very familiar. The ERI ones will be very familiar from what you've already heard over the last couple of days. The first one is embedded microsystems intelligence and localized processing. There are 3 sub-themes associated with that. Let's talk about those. The first one is increasing information processing density and efficiency. And what this really speaks to is having the ability to process signals, to process information with less energy. And you may want to do this for either of a couple of reasons. Either it's because you're interested in processing information at a leading edge, and so the amount of power, for example, that you have available to you is very limited, so you want to process a lot of information maybe with less than a watt. Or perhaps you're interested for other applications in very large computing, but you're limited by the total massive amount of computational energy required to do what you need to do, like in a data center. The second area is making decisions at the edge faster. And what this really is about is one step above what I talked about a second ago. It's not signal processing anymore. What you're really talking about now is making decisions. So as you might expect, this is more associated with artificial intelligence and trying to make better decisions and make it more quickly than you were able to in the past or that your adversaries can do. And the third area is, I like to say, a problem of our own making. It's a problem born of our own success. It's reducing the glut of digitized sensor data. So we live in a world now in which tremendous amounts of information can be digitized, and they can be digitized locally. They can be digitized at a sensor. I'm showing an example here on the right of something that can produce a tremendous number of bits from just a single sensor more bits than can easily be processed by a centralized processing unit. So how do we reduce that amount of information down to the essential parts that we care about? And so that's the third of the sub-thrusts. The second area that I'm going to talk about is next-generation front-end technologies for electromagnetic spectrum dominance. And this, I like to say, is really the traditional area that MTO has been engaged in since its creation, making front-end elements that have exceptional capabilities. Sometimes those capabilities are linearity, power. Sometimes those capabilities are bandwidth. But things that are above and beyond what can be found in commercial off-the-shelf electronics. So some of the three sub-thrusts that this include begin with reducing the size, weight, and power, the SWaP-C, and cost, the SWaP-C of front-end components. Really, this is talking about making things that are large, much, much smaller. Ultimately, we would like to make things like the LiDAR system, the big bulky LiDAR system, which is shown on the left, and is found in automotive LiDAR, for example, autonomous vehicles, much, much smaller, chip scale, if possible. The second area is increasing the tactical range of systems. And from the standpoint of the front end, this really comes down to two things, transmit and receive. So on transmit, can you transmit more power? And on receive, can you detect more in a superior way? Can you have what is often called lower noise figure? So better transmitters and receivers. And on the right-hand side, we have a set of problems that is emerging having to do with robust operation in congested spectrum. This chart shows a spectrum allocation that the United States uses. It's familiar to many of us. It is how, for a generation, multiple generations, we have divided up the electromagnetic spectrum for specific purposes. That's changing, and it's changing very radically. So now we have a world in which we are using spectrum in a much more flexible way, in a much more dynamic way. That presents all sorts of challenges and opportunities. Third area is microsystems integration. Now, integration, as I mentioned before, usually is thought and associated with the processes by which one interconnects and builds systems on a chip or builds systems generally. But here we've expanded the definition to include things beyond that, specifically trying to think about design and security. So really three problems, and they kind of break out into the three areas that I just mentioned. First, overcoming the inherent throughput limits of two-dimensional electronics. Electronics, as we've already talked about at the summit, electronics has for years been confined to two-dimensional surfaces to die. We're moving into the 3D world in which electronics is inherently a three-dimensional thing. And the reason why we're doing this, and we believe it has to be done, is limited by throughput. It's limited by the number of interconnects and the total amount of information that can be passed through those interconnects. So by going to 3D, we have a topology which supports a higher degree of performance. The second thing is another familiar problem at the ERI Summit, and that is the skyrocketing costs of electronics design. So as the number of transistors has exploded, gone from small numbers, thousands, even tens early on in Moore's Law, to now billions, many billions, the cost of designing circuits has become prohibitive for the Department of Defense and for much of industry as well, except for the very highest number of elements type manufacture. So how do we deal with the world in which small volumes need to have access to the highest performance, latest node silicon? And then the third area is an enormously challenging area for us and for the world generally, which is dealing with the threats that we see emerging in hardware security. And here what I really want to emphasize is that we have to deal with an entire range of threats, everything from Trojans to design threats and so forth. But we have to do it not at a single point in the life cycle of electronics, but throughout, such as manufacture, for example, but throughout, everything from design through sustainment. And so that leads to a very broad need to look at security across a wide area. And finally, as I mentioned already, there is a fraction of our office which is devoted to actually building microsystems for specific purposes. Really, those cluster into 4 areas. And those 4 areas are, first, communications, particularly communications associated with things like 5G. This is driven by a need that we see in the military environment, but also in the commercial environment, to ensure that communication links, your cell phone, for example, but communication links of all kinds, are sustained in a continuous way and are ubiquitous, because networking has become important for all domains. The second area is electronic warfare. So by reducing latency in electronic warfare, what I'm really talking about is making decisions faster, having the ability to cognitively understand the environment that you're in and take the appropriate actions. The third area is in generating and directing high-power radiation, lasers, but also more than just lasers. And the last area is a set of technologies that are associated with positioning, navigation, and timing. So understanding where you are and being able to deliver good timing in an environment in which the global positioning service is potentially not available. Okay, so those are the areas that we do broadly, including ERI and also the non-ERI topics. I'd like to spend just a few more minutes talking about how best to engage with us. And this is really focused on those of you who are potentially performers and wish to be performers on DARPA MTO programs. So I think the most important message about DARPA, if I was really going to point at one thing, is presented in this slide. And I would ask people to keep in mind when you deal with DARPA the P in our name. Defense Advanced Research Projects Agency. It's really about projects. So a project is motivated by a specific problem, right? So we are organized to address specific problems. So when you deal with DARPA, it is very important before you talk to a program manager, for example, to think about not just the technology solution that you're going to offer, but to think about what problem you're trying to address. That's exactly what the program manager will be most focused on. And the other key thing, which really subsumes what I just said a second ago, is the Heilmeier catechism. If you're familiar with Heilmeier, he was a former director of DARPA and very famously put together this very, very simple 5-question recipe for designing how one should do research, not just at DARPA actually, but in general. And it certainly was applied and at that time and is still very much used at DARPA to prioritize and make decisions about how we choose which efforts to fund. So it's great to be aware of these 5 questions, this catechism as it's called, but also to have answers to as many of these questions as you can, again, when you're addressing DARPA program managers. So generally speaking, there are 5 ways in which DARPA funds performers, and these are shown here. Probably, without any doubt, the most important way is through large programs. So programs can be of all sizes, sometimes relatively small, a few $1 million, but they can be very large. It says $50 million, but there are certainly many examples of programs that are in excess of that. A typical DARPA program might last about 4 years, again, with a range. But the key thing you want to know is how do you find out about these programs, and that is through what's called a broad agency announcement, or a BAA. They're published, and programs are invariably about solving a specific problem of national security interest. Again, the P in DARPA. So that is the most important thing. And many of the other rows on this chart can be understood in relationship to servicing programs from our perspective. Seedlings, for example. Seedlings are early studies that ideally lead to programs, or at the very least answer questions that a program manager needs to have in order for him or her to define a program. They tend to be much smaller, and it's critically important if you're going to propose a seedling that you understand that the duration needs to be fast and that it ultimately should be connected with a program idea. So if you're interested in a seedling, you should be talking to the program manager not just about that seedling, but what that information will help lead to. There is a particular BAA, often called the office-wide BAA, which is published every year, and this is the vehicle that you use. Responding to that BAA is the vehicle that you use if you're interested in seedlings. But the most important thing, and in general, this is going to be true for everything I'm going to talk about, before you submit a seedling, you should engage directly with the program manager to get a sense of what he or she is interested in. The third area is something you've heard about at the summit already. It's called Microsystems Explorations, MUIs. Those are cross in between. They're not quite programs. They're smaller than that, but they're a little bit more structured than an individual seedling. Typical award is $1 million or less, and typical period of performance, in fact, is always 18 months. And those are organized through what's called a PA, which is another vehicle similar to a BAA. The purpose of MUIs is to do early foundational work to understand new ideas and address new ideas, ultimately with the idea, again, that if successful, these may lead to future larger scale programs. Beyond that, there are two other sort of more specialized ways in which to deal with DARPA, SBIRs and STTRs, like other parts of the federal government. We have available money for those purposes. The rules here are very similar to the rules for any other organization that has SBIRs and STTRs. So you have to meet conditions like, for the case of a small business, for SBIRs, you need to be a small business and meet those qualifications. And you find that generally the rules and the way in which we operate are very similar. However, we're a little more flexible than other organizations in the sense that we compete SBIRs and STTRs year-round. So once again, the key step is to go engage with a program manager in an area that you think might be interested in the topic that you happen to be interested in. And lastly, we have a particular program that's called the Young Faculty Award, which is a way in which we like to recruit younger faculty. It's not limited just to academic organizations. The definition is somewhat broader, but really it amounts to researchers who are early in a field for them to explore specific ideas. And you can find information on that in its own BAA, which is actually administered by our partners in the Defense Sciences Office. So in every case, the key message here is if you are interested in working with DARPA, you want to directly engage with program managers in the areas in which overlap with your technical area. MUIs, I've mentioned already. The key thing is the 90 days, and I think a lot of this we've covered, but I included this just to give you a specific reference to that particular program announcement. And here I've shown a few examples of MUIs that we've done in the last year. So talking to a program manager is where I'm going to end up. How do you know who to talk to is a constant challenge. The best place to begin is to look at our webpage, www.darpa.mil. See if you can find someone from the description whose technical interests appear to overlap with your own. Then contact them. PMs are invariably interested and available for technical discussions and will try and engage with you. But if I may, let me give a couple words of advice. Keep in mind that program managers are really looking for projects. They're looking for programs. They're going to be excited about your latest technical result, certainly, but only if you can put that in the context of how a new program could be inspired or could result from this interesting technology development. And so I think when you present your ideas, you probably want to construct them in a way that appreciates that that's what they're looking for. Program managers are always thinking about the Heilmeier catechism. So as many of those questions that I mentioned before that you have insight to, try and answer those for the program manager and help him or her think through what that means. I like to say that PMs are best when you do their homework for them. So it probably is best to do their homework, or at least as well as you can before you engage them. And finally, it's important to listen to them. Program managers hear a lot of information, a lot of ideas are thrown at them, and they have a lot to process, but they have a lot of insights too. So it's important not just to be on transmit, but also to listen to what the program manager is trying to tell you. So that's sort of a whirlwind view of the office. I wanted to end really with this, the most important slide. I think you have seen this already, but this is the current crop of program managers in MTO. These are exactly the people, the ones in the second and third row, that you want to go talk to about technology areas and hear a few words are said about each program manager, giving you at least an insight into what areas of expertise they are most interested in. And with that, I believe the plan is to spend the rest of the time we have available to answer your questions. Okay, very good. Welcome to DARPA. We are here live in the auditorium here in the DARPA building. And for the rest of the session, what I'll be trying to do is to answer any questions that you might have about DARPA. And in case it's not obvious, you can submit your questions by typing in the box. It should be just below me, just below the video that you're watching right now. And we'll spend a few minutes answering those questions, and then we'll move on to the MTO Symposium part of the day. So let's begin with a few questions. So first question is, what impact has the advancement of machine learning and AI had on your programs and ideas for new programs? So this is a really good question, a tremendous amount of impact. During the time, I was in MTO about a decade ago as a program manager. And AI, of course, has a very long history, much longer than a decade. But what has changed, I think, the most in my experience has been the fact that when I was in MTO the first time, AI was much less capable. And what that means is that we now can imagine programs and setting objectives in which a tremendous amount of capability for decision making exists right at the edge. And I hope you saw a lot of that in the words that I was talking about earlier. So it has affected the nature of what we are doing. We still remain a very hardware-focused office. And so relative to AI in particular, we tend to focus more on the implications of the hardware implications of research. But in terms of using AI, the latest AI is very much pervasive in our office, and I think all throughout DARPA. So tremendously important. Okay. Next question is, how have non-traditional contract vehicles impacted the types of performers and work that MTO is able to fund? So what's being referenced here, I think, is what we call other transactions, OTAs or OTs. And I believe DARPA pioneered other transactions, much like in a previous time, DARPA pioneered the vehicle that's called a BAA, Broad Agency Announcement. But other transactions are ways in which non-traditional performers can bid to DARPA programs and obtain funding. And many of these non-traditional performers are not accustomed to meeting all of the requirements that are necessary in order to bid to a government procurement. It's a way of allowing flexibility in contracting. It's been tremendously popular at DARPA. It has increased very significantly over the years. It is what has allowed us in ERI to solicit and involve so many organizations that have not been involved in DARPA programs prior to that. I should also say that another aspect of other transactions that's really important is if they're crafted in a particular way, they can be very, very fast. And so you heard me talking about MUIs before, these microsystems exploration projects. MUIs are only possible because we use other transactions. Otherwise, I don't think it would be possible to contract them as quickly as we do. So OTs are really important. They're something that we look at as a opportunity for us, something to be very careful about and to use appropriately, but it allows us to reach out to a much broader community. Okay. Next question. What advice would you give someone who was interested in becoming a DARPA PM? That's a great question. I guess you might want to talk to the PMs when the PMs come up and we get to the second half of this discussion. Recruiting is a really hard thing at DARPA because we have such a large amount of turnover. About 25% of the program managers leave every year. And so we are always looking for talented, bright individuals to come. We try to address a range of opinions or diversity to try and solicit new ideas. That's why DARPA has traditionally had such large turnover. It's something that we do very consciously. When we're involved in recruiting, the thing that Deb Palmer and I spend most of our time doing is really trying to ensure that the program manager or the potential program manager is really focused on new ideas, new problems. You saw me talking about that a few minutes ago. The P in DARPA, the projects. I like to think of DARPA as an organization that is really focused on trying to identify what are the compelling new problems that we need to deal with, and not necessarily having all of the answers or most of the answers in terms of what those technologies are. The best advice that I can give is to someone interested in DARPA, other than come talk to us, is really think about what that problem is or those problems are that really will change the world. And then tell us why you think they're likely to change the world. And so that's something that I think is easy to say and we know very hard to do. Okay, next question. How has COVID-19 impacted your programs and BAAs? So, like a lot of places, we've been very challenged to try and maintain momentum and stay in business during this rather difficult time for the country. And I think we've done reasonably well. We depend on a lot of people, especially our performers. And many of our performers, particularly educational institutions, have been closed, have not been able to move forward. But most of them have been working in one fashion or another. And so there is a case-by-case answer to this question. Program managers have been working with their performers on existing programs to try and minimize the impact, deal with the impact, and allow work to continue as best we can. And I think we've actually done fairly well in that regard. The other half of this question really was about BAAs and new solicitations. Well, we have not stopped in terms of our interest in developing new program ideas, advertising them, soliciting them. We've had source selections for new programs, and we continue to move pretty much at the pace that we always have moved. Typically, this time of year, the last few months, is a slower period for new starts, for BAs to come out. So there haven't been perhaps as many as if it had been a different time of the year. But I expect that will change over the next few months as we go into what is more traditionally a busier season for us. Is there information on upcoming MUEs or BAs at this meeting? And the answer to that is no, not specifically. Again, the best advice, as I said over and over again in the last few slides a few minutes ago, the best advice I can give you is to contact program managers and engage with program managers to try and gauge what they are interested in and what they're working towards. But in the interest of fairness and the interest of making sure that everyone who responds to a BAA has an equal amount of time, we don't announce in advance. The way in which we do announce those are through solicitations. That one table in that one slide that I showed before shows that you can look on our webpage and it will tell you what the latest solicitations are, and you can react to those at that time. You should, however, from this meeting get a sense from some of the comments that the program managers are engaged in, some of the ideas that they're thinking about. This is never an assurance that there will be a program. There may not be a program in some of the areas that you're going to hear about ever, or there may. But certainly everything in terms of program development at DARPA starts with the program managers, so it's good to know what's on their mind. So you'll get a chance in just a few minutes to ask some questions of them directly. Next question. Can Canadian companies apply for DARPA grants? Yes. In fact, for the most part, internationally, anyone can apply for a DARPA contract. I won't quibble with the word grant, but for a contract, you can be from any part of the world, and that, of course, depends and varies on the nature of the specific BAAs. If there's classified work, perhaps not. But in general, particularly for more fundamental research, there are many, many examples of universities and companies from across the world that are involved in DARPA programs. So the next question is, how do we, I guess, determine the right amount of money for a program? That's a tricky question and a tricky process, actually. There is no easy way to do that. Again, we engage with the community broadly, try to get a sense of what the challenges are for a particular topic, and get a sense of how hard those technical challenges will be to get essentially a level of effort that we anticipate, and we'll budget. Sometimes we get it right, sometimes we don't get it right. One thing that I will say here, and if we don't get it right, we have opportunities to correct ourselves and to reset our plans. One thing that I will say is that most of, nearly all of the programs that you're going to find in MTO, maybe as opposed to some in the other offices at DARPA, have multiple performers. And so there is some flexibility if bids, proposals come in at a higher amount than we anticipated, to structure by having more or fewer performers on a particular program. Next, what is the expected concept TRL at the start of a new program? That's a good question too. So that's going to depend a great deal on the individual technology involved. It's also going to depend on the office. But in MTO, you would typically expect something to be beyond TRL 1. You would expect to have some evidence that there is a path forward, and something that TRL 4 or 5. I guess perhaps I should explain what technology readiness level is to people who are not familiar with that term. I believe this was a term that was developed by NASA, but is now commonly used in the research community. And there are levels that are associated with the state of technology. A TRL 1 is essentially proof of concept, early demonstration, and so forth. And by the time you get to, I believe it's TRL 9, you have fully vetted that the idea that you're developing works and works reliably and so forth. We're in the middle. We're typically, a typical MTO program would probably start at 2 or maybe 3 and get to 5, demonstrate that it works, but not necessarily be re-engineered, packaged, and ready to be transitioned in exactly the form that it is. What we're really about is removing the biggest technical barriers, the technical challenges that I was talking about a second ago. So that really pushes us towards the center of that TRL list. Next question, is it required ERI programs use and develop open source software and architectures? Open source software architectures. No, it isn't. And that's going to depend heavily on the individual program. Some programs that may be a true statement, but in general, you as a bidder into a MTO program have the ability to select which particular approach you're going to use. There may be advantages. It may be a more attractive proposal in some cases to use open source architectures, but it's certainly not mandated. And where it is mandated, I think that should be clearly called out in the BAA. Do you need to be a U.S. citizen to become a DARPA PM? Yes, you do. And in fact, you need both to be a U.S. citizen and to be able to obtain a clearance so that you're able to look at things that are classified. So PMs do have to be citizens. Okay, what is the interplay between system-level projects and MTO programs? So I'm going to kind of assume that the thrust of this question has something to do with how do we engage with our sister offices, the systems offices, particularly the STO and TTO, the Strategic Technology Office and the Tactical Technology Office. And the answer is we engage with them a lot. By the way, by no means are they the only systems offices in the world. We engage with systems offices in many, many other organizations outside of DARPA. But I get a sense that that's what's being asked here. How do programs within DARPA interplay with one another? And the answer is we tend to be a little bit more component focused. We tend to be higher risk. So technologies that are ready for a STO or a TTO to embrace, I'd like to think they should embrace, and we welcome that. Many, many very positive examples of technology transition, of ideas that came out of MTO that formed the basis for programs in some of those, in either of those other two offices, and that's great. In other cases, though, when we're not ready for that, when the technology is not ready for that, we've increasingly shown a desire and an interest to take on the responsibility of doing demonstrations of applications. You saw that a few moments ago in some of my slides. So in specific areas that we care about, areas like communications or PNT, we do move forward on what I think could be regarded as system-level projects of our own. What is the preferred engagement model for program ideas that span multiple PMs? That's a good question. Not one I hear all the time, actually. And that can be tough. Identifying, if you have a really good idea, a really good thought that you think could lead to a DARPA program, and you'd like to see DARPA get excited about it, we often get the question, who should I go talk to, or how should I go find that PM? Again, the web page that we have is probably the best starting point. And then from that, I think you can learn more about the existing programs of whichever program manager it happens to be. But there will be these situations in which it looks like 2 or 3 or even 4 program managers might be overlapped and interested in your particular technology. What I would encourage you to do in that case is contact all of them. Probably it's best to make clear to them that you are contacting other PMs. They don't, by the way, necessarily all have to be in MTO. They could be in other offices as well. But program managers relatively rarely structure multi-PM programs. So it's probably best to ask around and talk to various people. I think you'll get a sense very quickly about whether you've struck a nerve, you've identified something that a PM is interested in or not. Very, very often when you reach out to a program manager, he or she might say, I'm not interested in that, but here's the name of a person you might want to go talk to instead of me. They tend to be very cooperative in that regard. Are there plans for hybrid biological electronics programs? That's a great question. So we have an entire office in biology, BTO, Biological Technologies office. That started a little bit more than 5 years, maybe 6 years ago. What a lot of people don't remember is that that office came out of, in part, the Defense Sciences office, but also our office. About half of the program managers in the original version of BTO were from MTO. At present, I don't think we have very many, if any, programs that I think heavily overlap in the biological sciences. But there has been a lot of interest, particularly recently, even before COVID, but especially because of COVID. A lot of interest among the program managers in moving in that direction. We have a different skills, program managers in this office have a different skill set than the ones in BTO. And I think in some ways very complementary. Perhaps I'll contradict myself from what I said in the last question, because this, it seems to me, is an area that's ripe and could perhaps benefit from a collaboration between, say, a program manager in BTO and a program manager in MTO, depending on the circumstances. But it's very much a case-by-case situation. So again, if you have interests and you think you're at that interface between the two, go talk to a PM. Okay. Thank you. What is MTO's plan regarding the CHIPS Act? Our plan regarding the CHIPS Act is to read the newspaper and follow what's going on. We are excited about CHIPS. We are excited. We are very enthusiastic that the need to improve the situation that we face in this country in microelectronics is widely understood and increasingly appreciated. That's very gratifying to us. It's very much connected to ERI. But our job in the R&D world that we live in is to execute to the resources that we have, and that's what we're doing in ERI. So we're very anxious and interested to see what happens. But in terms of a plan, our plan really is to follow the newspapers. What is DARPA's stance on trusted electronics? DARPA's stance on trusted electronics is that there are research tools necessary to ensure that electronics is trusted. And our job is to try and look at those tools and understand what research is possible that will enable us to have a better sense of how secure electronics is regardless of where it's manufactured. And so in that sense, I think, again, we are very interested in a lot of the decisions that are being made about trusted electronics at levels higher than us. and of course will be affected by those decisions. But regardless, I think we have a role and a responsibility to play to choose technology topics that we can go after, which will benefit and really help enable a greater sense of trust. DARPA was key in the development of gallium arsenide and then in gallium nitride. What's next? So that's a question I've been hearing for a long time, and I have an opinion about it. I can tell you my personal opinion. There's a sense when one asks this question that the answer to this question is a material answer. So we developed a material, we developed a second material, the next technology must be a third material. And that almost certainly is true in a sense, because there are a lot of really interesting materials right now, electronic materials that are being developed. But I think it's also a little bit misleading. I would say that the thing that's next is 3D integration, the thing that we are, the revolution that we are in the midst of right now. That's very disruptive. There will be better materials and newer materials, but I think it's a little bit of a mistake to focus only on materials development as driving what happens in electronics development. Good? Okay. And I think at this point we are out of time. Is that correct? Okay, good. All right, so without further ado, I think the plan then is to move from this MTO 101 session to the MTO Symposium. So in case you missed any of this presentation or in case you have other questions that you didn't get to, I'd like to point out that this session will be repeated tomorrow at 2:15 Eastern Time, but will be given by Dr. Deb Palmer, our Deputy Director, and so he'll be hosting that session. So now what we're going to do is we're going to proceed to the MTO Symposium part. And what we're trying to do here is to discuss some of the research that is beyond, outside of, extends past what we're doing in ERI. And so I'm joined here in the auditorium with, I guess, 7 of our program managers, the faces that you saw on that one slide. And most of them, maybe all, no, most of them have programs and interests in areas that you haven't heard about yet from the speakers in the plenary sessions. So let me explain just a word or two about how this is going to work. What I'm going to do is introduce each of the PMs one by one, and afterwards they'll come up and they'll give a short presentation talking about some of their interests, some of the things that they've been working on, or some of the things that they're thinking about in the future. And after that, just as you had a chance with me, we will have a around the room panel session in which you get to ask questions and answers from you. Okay, so let's proceed. And the first up, it's my pleasure to start with one of the newer faces in the office, Dr. Dave Abe. Dave joined us from the Naval Research Laboratory earlier this year, and Dave's interests include vacuum electronics and high-power RF amplifiers. So he runs right now 2 programs that he inherited. One is called, we call it M-Cubic, but it's magnetic, miniaturized, and monolithically integrated components. And the second one is called Havoc, which is high-power amplifier using vacuum electronics for overmatch capability. So Dave?
Thank you, Mark. So the core mission of MTO is to provide technology to ensure that the U.S. maintains superiority in 3 basic areas. One is C4ISR, one is electronic warfare, and the third area is directed energy. So yesterday and for the rest of this week, there's a lot of information and talks on what we're working on for the C4ISR part, but for something completely different, I'd like to talk to you about directed energy now. In particular, I'd like to talk about high-power microwave technology. And because many of you may not be very familiar with this technology, I'd like to just spend a couple of minutes to give you a brief overview and some background on what HPM is. It is considered a subset of electronic warfare. However, it really is distinct from what we normally consider electronic warfare and electronic attack. The goal of electronic attack systems is to jam or deceive enemy sensors. In contrast, in the case with HPM systems, the goal there is to use coherent electromagnetic radiation to disable, to disrupt, or damage targeted electronics or electronic components. The advantages of an HPM kind of attack are that, for one thing, it has a wide area effect, and it has a potential for a wide area effect over a fairly long range. So in this case, it does not require precision targeting and aiming for the attack. It operates at the speed of light, and it also has a potentially deep magazine. As long as you have energy storage and power, you can keep shooting. And in addition, it also is capable of operating in adverse environments, so it will operate in fog and dust, for example. These features give you a complementary capability in a layered defense scenario where it complements and augments, say, a kinetic kill and a electronic attack system. For example, for defense of things like air bases, fixed infrastructure, ship-based self-defense. In addition, because the technology is also non-lethal and non-kinetic and has low collateral damage, it also is useful in operations, what used to be called operations other than war, or pre-kinetic and stabilization operations, the so-called gray zone now. And for there, it could be used for, say, counter UAV or vehicle stopping or vessel stopping, where you don't necessarily want a lethal response to things. The way that it works, if you look at the graphic on the left side of your screen, there are two basic mechanisms for HPM attack. One is front door, and that's where the electromagnetic radiation couples in through intended apertures such as antennas. In this case, typically the target is the missile seeker, and it's the receive side, the low noise amplifier in the missile seeker. This can be very effective, but because it's targeted toward a particular frequency of the antenna, the systems that are geared for this tend to be single use for a particular target. A more broad range of targets can be gotten by backdoor attack systems, and in the backdoor attack, the electromagnetic radiation couples in through unintended apertures, such as seams and cracks, cable runs in the body of the enclosure. In this case, as I said, it can be more applicable to a broader range of targets. However, typically it requires more power because you have to overcome the attenuation of getting inside the target. Unless you go in with smarter modulations and make use of frequency agility, and so I'll be talking about that in a little bit. So that is the vision and the challenges. The vision and the challenges for the directed energy programs that we're developing at MTO are to create these sources that will have increased range and probability of effect. And as I mentioned, the way to do that is to exploit amplifiers that do have the frequency agility and the waveform complexity that you can really exploit target vulnerabilities. In order to do that, we also need a better understanding of the predictive, of how the energy couples into the targets and how they create the effects on the electronics. And for that, we need fast predictive models for engagement analyses and waveform optimization. Those are two key challenges, and in addition, amplifiers also bring the possibility for scalability. We can power combine and increase mobility, so the individual systems can be small to increase the ability for transportability. And as I said, the interest in backdoor attack is for multi-mission impact. HPM systems today are oscillator-based, meaning that they're very high peak power, but also very narrow band with little or no tunability. The applications include counter unmanned aerial systems, vehicle and surface disruption, electronic strike, so against commercial and defense infrastructure, and guided missile defense. On the right-hand side of your screen, there's some examples of some recent experimental demonstrations. At the top is the AFRL CHAMP system. You may have heard of this and seen it in the news. This is an HPM source that was deployed on a cruise missile. The cruise missile was then able to fly out to a target, loiter long enough to get multiple engagements against a variety of electronic systems that were located in mock buildings. In the right-hand side is the AFRL Thor system. That's a tactical system for counter UAS, counter unmanned aerial systems. That was built for portability, and all of that system that you see there, including the antenna, fits in that 20-foot connex. It's able to be transported to remote locations, and it can be set up in a matter of hours by a handful of technicians. And then finally, there's a graphic that depicts small vessel disruption using HPM. So again, it's a non-lethal application for the technology. But the limitations of the current state of the art are that it's narrow bandwidth. And so, as I said, you don't have the ability or the frequency agility to be able to optimize the coupling into the enclosures, nor do you have the ability to use waveform complexity to be able to really exploit the vulnerabilities in the electronics and the circuits. Also, the maximum peak power, output power, we've reached about the limits, the physics limits of what we can do in a single device for these oscillator-based systems. Electric field breakdown, we're reaching that limit that we can't go to much higher power. So we have to be smarter about how we're using these systems to attack electronics. And then finally, the effects, our understanding of effects on electronics is largely phenomenological, meaning that if we have a new target that we want to look at, we often have to take that target, put it in an anechoic chamber, or take it out into the field and be able to, and just do the experimental work to characterize it. We need to move from that paradigm to one where we're actually getting a predictive capability in simulation that will allow us to get a lot more understanding of how the effects happen. And so those are all DARPA hard problems, and so not surprisingly, that is what is informing our approach to the new technologies that we need to advance HPM technologies. And so in summary, that's high power, ultra broadband amplifiers that have the power to create the range, but also the bandwidth capability to do the frequency agility, agile waveforms to exploit target vulnerabilities, computationally efficient physics-based simulation tools to model the electromagnetic interactions with the targets. Here we can take advantage of advances in electromagnetic theory and computational techniques that have happened in the last 5 to 10 years. And then finally, compact power, because power is often the largest component of any system. That, in a nutshell, is what we're looking at for directed energy. I hope I've given you a flavor for the technical issues and where we're heading. I've had an opportunity to engage with a number of you already, and I'm looking forward to working with you in the future. Thank you.
Okay, thanks, Dave. Next up is Dr. John Burke, who's a familiar face to us at past summits. He's been in the office for a while. His interests are in quantum sensing and in positioning, navigation and timing, PNT. He's got a bunch of programs. Very quickly, I'll just mention Atomic Photonic Integration, APHI, Atomic Clock with Enhanced Stability, ACES, Atomic Magnetometer for Biological Imaging in Earth's Native Terrain, AMBIENT, and Quantum Imaging of Vector Electromagnetic Radiation, QUIVR. John.
Thanks, Marks. So I'm going to talk a little bit about quantum sensing today, and quantum being rather infamously difficult to gain some intuition about. Maybe I'll spend at least one chart just outlining some of what we're talking about. So, and also why you might actually care about this from your walk in the woods. So I'm not going to try to explain what a quantum system is, but there's some box somewhere for today's purposes that has some particles in it, maybe that typically electrons that are bound to something. And there's some frequency sources, probably a laser, that we're using to probe that system and make some kind of measurement. And the trick we're playing is that the world around this quantum system, electric field, magnetic field, maybe an acceleration field, gravity, will manipulate that system, and we can make some measurement. And I'm going to try to talk to you a little bit today about why that's a good thing. If you're making similar kinds of measurements in whatever system you're probably using that's commercial, is probably limited by a number of things that the quantum world doesn't have to necessarily obey. So things like thermal noise, where in the quantum world we're dealing with particle statistics for the most part, which you can get a large advantage in. I've got a little, maybe a provocative number there to point at. In your device, you're probably dealing with engineering challenges, material tolerances, and so on. Whereas in the quantum world, these frequency sources end up being the limiting factor as far as how fabricatable or manufacturable these things are. But in principle, they can be very, very good. Making lasers with 16 decimal places of precision is sort of quote unquote easy today, at least at laboratory scale. And finally, your system's probably limited by wave properties like wavelength, and maybe forcing a certain size for your system, where in the particle world, we're fundamentally limited by the particle size and the scattering and interactions of those systems. And those things can be quite complicated, but just kind of giving you a flavor of why we might be investigating these kinds of systems. So you may not know a lot about the history of this, but one of the first things I did when I came to DARPA was try to collect all of that, and so here it is in public release form, at least for quantum sensing. And I just want to highlight the chip-scale atomic clock program was one of the first programs that really kind of started this thread into quantum technology to make an atomic clock that you could actually buy for a reasonable price and put in a reasonable size and power. And that really launched a whole thread of ideas that has kind of brought us to today that I'm going to highlight a few things from. There's sort of two broad thrusts here I'm kind of showing. One is I'm calling it tactical systems, electromagnetic systems, and one of them is sort of often led by DSO, Defense Science Office programs, to really realize the highest performance possible. And I'm going to briefly mention that too in the Atomic Photonic Integration program. So just to kind of give you an idea of some of the things that are happening now, Mark mentioned the Atomic Clock of Enhanced Stability program, or ACES. I'm not going to go into a lot of detail, but we're at the point now towards the end of that program where having GPS level timing, that's about a nanosecond, that fits in the palm of your hand is actually possible. And so we're excited to see that program transition into hopefully something you could buy in some few years from now. In addition to that, we have the ambient program that Mark also mentioned. Here, not going to a lot of details, but this is a program where you're trying to sense the small magnetic fields that your neural pathways make when you're actively thinking, and you can actually see this in real time. This is a medical technology that you could actually find in many large hospitals, but it's hard to actually use in sort of at reasonable price, and especially you couldn't use it out in the world, like if you went to put it in the back of an ambulance, say. So we've actually had some recent progress here where you can actually see as a person standing there, sitting on a bench out in the field, out in the real world, and you can actually see the auditory response of this person after some averaging. And so this is showing that you can actually see neural signals out in the real world, and this could be tremendously valuable for things like diagnosing traumatic brain injury. So I hope someday to see something like this, on the side of a football field, or maybe able to diagnose traumatic brain injuries for a soldier that maybe has encountered an IED or something similar. So this could be a tremendously powerful technology. I want to kind of go on to the other thread, the Atomic Photonic Integration program. So, these really high-performance quantum systems are rather complicated. There's not just one frequency source or laser, there's a bunch. So I'm showing you a picture in the middle from the best atomic clock, or one of the best atomic clocks at NIST, the National Institute of Standards and Technology. And you see all these visible lasers, and it's very pretty, but it's pretty unwieldy to try to think about using that in sort of the real world. So here's an artist's version of what we might try to do, where it's all on a chip, where you have miniaturized visible lasers, sort of a photonic circuit to route and manipulate all these laser beams, and finally some kind of system where you could actually project those lasers onto a quantum system, say some atoms or ions that are trapped above the surface of this chip. So briefly, I'll just point out there's this Lumos program that Gordon Keeler is managing that is going to be very helpful here. But AFI is really working on the things to the right in this figure, the sort of routing circuit and this projection circuit. And you can see some early progress. This is a new program started, we're about halfway through phase 1. But here's an image from MIT Lincoln Lab where you can actually see a photonic circuit. You can see all the traces routing 7 different laser colors around and going through several different processes to eventually project them onto 4 ion trapping sites. You can see the bright spots there. And so this is very, very fascinating, very important work moving forward. We have some other results too, really showing that you really could manage to miniaturize these things, maybe even more so than other atomic clocks and other quantum systems, and make something that's actually fabricable at, in say, some kind of fabrication facility. So I'm pretty excited about this. I think we're making a big progress moving forward. So a lot of people are interested in what's going on next. So I want to spend most of my time talking about what where I'm trying to go next. And that is to take on the mighty antenna with a quantum system. So this is sort of outlining some of the sort of limitations or at least metrics you might see in a classical antenna. I'm picturing your monopole antenna you might have attached to a car or something. So if you're trying to have a broad frequency access with that, getting to sort of 10-to-1 frequency access, say an antenna that works from 1 to 10 gigahertz, is doable, of course, but challenging. You'll probably give up some other qualities you might care about. Meanwhile, these so-called Rydberg sensing technologies, there's a paper on the right you can look up. These things have been demonstrated to work over at least 1,000-to-1, so from megahertz all the way out to terahertz. So with the reprogrammability, again, assigned by the lasers. So tremendous potential advantage from a broad receiving point of view. Sensitivity, right? Most after you consider the aperture size, you usually run to a thermal limit, Boltzmann's constant, temperature times the bandwidth of your receiver. It's very difficult to get past that without, usually cooling your system as the main way for reducing the temperature. But quantum noise is not so hard of a limit. And it's a little bit hard to try to figure out what the quantum limit would be. It depends on many things, but research has shown that something like 10,000 times better than thermal limit is at least possible. So we'll be interested to find out how far that goes. On the power side, depends on many things. Again, for antennas and your receivers, how much power you could really take before you run into thermal problems. And the systems here, these are atomic gas systems, so you really have to think about ionizing the whole gas. And that's sort of kilowatt levels of power you'd have to apply in order to cause any problems. Again, huge advantage potentially. Accuracy can be important to a lot of things. And again, these atomic systems are very repeatable, maybe don't even need calibration, can operate much less than 1% as far as sort of the overall accuracy. And finally, the most important one maybe of all of these is the size. The well-known Chu limit limits, if you want to have some reasonable bandwidth and efficiency for your antenna-based system or your aperture-based system, you need to work at a size that's commensurate with the wavelength of the frequency you're trying to utilize. So that can really force you to pretty large systems. We're in the particle domain. We don't really care what the wavelength would be, but it's the atomic radius, which is exceedingly small compared to any of these things that we really would care about, and really more about the density of the atoms next to each other. So switching from waves to particles really gives us another potentially huge advantage in terms of overall size. This is pretty forward-looking, but I'm pretty excited to try to figure out where these different possible advantages lead to. And I just point out that this last point, the size and the Chu limit, there's a paper from Army Research Lab that I'm referencing there, where they look at that sort of megahertz class frequencies. And if you look at the channel capacity there, and you have to go read the paper to understand sort of the assumptions here, For about a 7-centimeter device, you're looking at like 6 or 7 orders of magnitude higher channel capacity in these sort of small frequency, small antenna limits. So that is a lot of promise here that is potentially ripe for exploration. And I'll take a seat. Thank you.
Okay, thank you, John. So our next speaker is also John Davies. He's another newer program manager in the office. He joined us in the spring from Leidos. He's got a range of interests. They include adaptive RF systems, artificial intelligence, real-time signal processing, and electronic warfare. Currently, he's going to say a word or two about, about his existing programs, digital RF battlespace emulator, Derby, and radio frequency machine learning systems, RIFMLs. So, John?
Thanks, Mark. Today, I'm going to be talking about RF decision making. All RF systems need to make decisions, and what kinds of decisions depends on the RF function, which could be communications, radar, spectrum sensing, electronic warfare, or multifunction combination of all of these things. Today, there are 2 approaches to RF decision making, and these correspond to the first and second wave AI technologies. At the top of the slide, let's first consider expert systems, where developers must think through and define precisely the intended operational environment and the rules or logic that we want our RF systems to follow when they're operating in these environments. And then we hard code these rules into either software or machine readable configuration files that can be parsed by this software. And this is that type of file is shown here as a decision plan. So what kinds of rules might we have to encode in these decision plans? Again, application dependent, but some common examples is that you need to encode which receive and transmit frequencies to use, how to manage your receive and transmit timing, how you choose where to point your antenna, as well as how you configure a transmit waveform or your receive side digital processing. And as we've seen in other presentations at the ERI Summit, modern software-defined transceivers are greatly expanding the degrees of freedom available to these RF systems and driving us to need much more complex rule sets to take advantage of these capabilities. And with an expert system approach, if we don't have a defined method to take advantage of these new degrees of freedom, then we may be leaving capability on the table. And then when we further expand to considering autonomous RF systems, we ask these systems to sense the RF environment, reason over the signals there, and adapt their behaviors in response to what they perceive. Planning from an expert system approach for all of these potential adaptive contingencies is furthermore very stressing. So what happens when we bring machine learning into the solution? Well, as shown in the bottom figure, rather than encoding explicit rules for how we want to behave, we ask the developers of these systems to curate data sets and then use these data sets to train algorithms that can infer the correct behavior from the labeled examples. And as we look at, and this can be faster to develop than expert systems, but I think as we look at both of these approaches, what they have in common is that the developed decision plans succeed when the operational environment is well within the design assumptions or the bounds of the training data set. But we can see performance shortfalls when we're operating in unanticipated environments or for unanticipated missions. And we may get really unreliable behavior under these conditions. And if we need to correct any performance shortfalls in these new environments, it takes a re-engineering of the capability, which includes an expert system case, rewriting rules, or curating new labeled data sets in the machine learning case. Both these things can be lengthy, and what further lengthens the process is the need to verify that this human redesign meets the new expanded requirements. These two steps in aggregate create a very lengthy process that substantially slows the deployment of new capabilities to RF systems. There's a need for a new set of approaches that will now enable decision plan generation to be accelerated to enable us to rapidly deploy new capabilities for new environments. So our vision is for a continuous improvement in RF decision making. We know that we cannot fully predict or control what types of electromagnetic environments we're going to be operating in. And this is particularly true of DoD applications. This makes it very challenging at the onset of a capability development to establish firm requirements for the behaviors that we'll need at that early stage. So rather, we need to develop architectures that assume we're going to be operating under uncertainty and build in the ability to rapidly update our decision plans in response to dynamic mission needs. And this slide here is presenting a reference architecture for just such an approach. And this must include adapting to dynamic environments, as shown in the right, as well as potentially changing operational needs as expressed through the intent of the operators shown on the left. And for these classes of architectures, if we don't get it right on the first pass, we have opportunities to improve performance on second and subsequent passes, so that we can continuously improve our capability without requiring the intervention of human developers. And there's two keys to this class of architecture that we're showing here. First is that we empower autonomous RF systems to audit the performance of the decision plans that they've been provided. So as shown in this red arrow in the center, we give these systems the ability to self-critique the instructions they've been given and provide this feedback into a process that can absorb it and lead to continuous improvement by allowing these systems to understand and criticize the limits of their own provided courses of action. Second, as shown on the left under decision plan generation, we need to aggregate these experiences into exploratory simulations where we can rapidly investigate new decision plans. The objective here is not necessarily to optimize our decision plans, but rather to provide sufficiency of these plans across the widest possible range of potential environmental conditions while minimizing the opportunity for failure modes. And this is particularly true that we need to minimize the probability of catastrophic failures in very stressful environments. There are multiple technical challenges that could prevent us from realizing this vision. Just a few examples is that we need to be able to structure autonomous systems to be able to extract actionable feedback from the environment that they're operating in. That's critical to enabling this feedback loop in our decision plan generation pipeline. A second challenge is the trade-offs between the fidelity of the updated decision plans and the feedback of the experiences from the edge, and the rate at which we overall update our decision plans. While in a perfect world with unlimited compute and communications bandwidth, we might want to vacuum up and record all the data at the edge and centralize that into our decision plan generation engine. in any practical or real-world constraints, we need a way to compress both the decision plans and the feedback of experiences so that we can achieve an update rate for this entire cycle that is still useful within operational environments. And then finally, another key technical challenge is setting the fidelity of the exploratory simulation inside the decision plan generator. This is necessary to both maximize the scope over which the exploratory decision plan evaluations can take place, minimizing the overall cycle time to create new plans, while ensuring that we can reliably transfer learned decision strategies from the simulation environment back into the real world and have some confidence that we're going to get an improved outcome when we actually use those plans. So to take a little bit of a step back, broadly, my research interests span the waterfront of intelligent sense and compute, particularly for RF and other sensor and end effector systems. And I'm looking to develop technologies that provide RF systems with the fastest possible reaction times over the widest possible receive and transmit degrees of freedom, fed by the best, most up-to-date information where it's needed at the edge. And many of these topics of interest I've already alluded to. We need real-time and faster physics-based simulation of sensors and end effector systems. We need really simulations that are fast enough to be used not just for system development, but to be embedded and used continuously as part of system operation. We need automated methods for decision program synthesis and verification. We need knowledge sharing, new knowledge sharing approaches among intelligent sensor and effector systems. And then, of course, we need robust methods for sensor data processing and fusion that can operate in highly uncertain environments. Finally, all of these needs, as well as the needs to reconfigure intelligent edge processors at waveform timescales, drive us to need new processing architectures to support these kinds of compute approaches. Please feel free to reach out to me to discuss new concepts on these topics or anything related. And I very much look forward to fielding questions on these topics in this afternoon's panel discussion. Thank you.
Okay, thank you, John. We actually are now right about the time for in fact, we're a little bit early, but it's about time for a scheduled break. So we're going to stop for about 15 minutes, and we will resume on the hour, 4 o'clock Eastern time, and talk to the other 4 members of our panel. Thank you. Welcome back. We are going to do the second half of the MTO Symposium. Before we do, just a comment. The floor is open for questions. So if you have questions, same procedure as earlier in the MTO 101 part. Just enter them in that little box below the video. And the questions you have can either be for individuals, feel free to direct to specific people, or it can be to just an open question for the group. And you can start sending in those questions immediately. And all right, we will continue now with our next speaker. It is Dr. Ben Griffin, who has been in MTO for a while. His interests include RF resonators and other MEMS devices, low power sensors, and high temperature electronics. And his programs include the Near Zero Power RF and Sensor Operations Program, N0 it's called. Ben.
Thanks, Mark. So I'd like to talk to you about an interest we've had and been exploring over the past year in extreme high temperature electronics. And this interest of mine was really born out of an experience where I was, in my prior career, developing sensors for high temperature environments. And we were focused on different aero platforms with extreme environments, things like hypersonic vehicles, turbine engines. And in these systems today, a lot of times we measure outside of the hot zone and then try and extrapolate information into the hot zone. This leads to inaccuracies, it leads to factors of safeties in the control algorithms with the system. And through this experience of mine, I was really frustrated by the lack of options I had in developing sensors. And much of that was because I had taken for granted the electronics capability I was used to having in a normal environment. And so when I arrived at DARPA, we started looking into high temperature electronics and what the possibilities were and how we thought we could impact this space. And as we did that, we quickly realized, well, we're really looking at a small piece of the application space, that really there was a lot more capability here, a lot more opportunity for impact. And these could be anything from improving the power or duration of our EW front ends, looking at the controls, electronics around our power systems. And so really it became much more broad than that. You can put electronics into a high temperature environment and get them to survive, but you could also consider unburdening the thermal management system. And that's really what we're focusing on today, is how do we create temperature hardened electronics so that we don't have to provide the same amount of thermal management as we do to get into these environments and into other platforms. So if we take a look at, well, what are really the technical challenges around creating extreme high temperature electronics, there's a series of questions you have to ask yourself. So the first and most obvious question is the semiconductor material that I have, is it suitable for the temperature environment I want to put it into? And you quickly realize, well, wide bandgap semiconductors like gallium nitride and silicon carbide have an inherent advantage over silicon because of the wider bandgap. And so we've leveraged really to this day and age lots of investments in these materials for other applications like optoelectronics and RF and power electronics. So those materials have matured to a level where we can now leverage them for high temperature electronics. But despite all this, we don't really see any or very few demonstrations above about 400 degrees C. And the question is why, and that leads to the second question. Well, do we have the materials and the integration that support these materials for electronics operating in the high temperature space? And this is where we start to find some of the challenges we face going forward. Much of the failure mechanisms at temperature over operationally relevant durations arrive in things like the gate dielectric breakdown, electromigration in the metal routing, dielectric cracking due to thermoelastic mismatch in the back of the line, delamination of the contacts. And so to go forward, we're going to have to address those problems if we're going to have a high temperature electronics capability. But even if we go do that and we go take care of the chip level integration and materials, enabling the chip to survive at that temperature, there's a third question to ask ourselves, which is, do we have the passive components and the packaging that need to exist to support that chip to operate in the high temperature environment? And there are also some challenges that are very similar in those spaces as well. So while the wide bandgap materials themselves are able and capable of operating at these high temperatures, it's really the challenges outside of, in terms of the materials and integration and how they interact with the semiconductor. That's where the challenges are today and the problems that we need to address to see high temperature electronics out in the space. And so if you take a look at really what those challenges are and what the potential opportunities are, I think there's actually a few different directions we can drive going from here. One of those at the extreme end is to maximize the temperature hardness of those material sets, to take our wide bandgap semiconductors and enable them to operate at the maximum temperature that the material is in and of itself allows. And on the screen there's a indium aluminum nitride GaN hemp that was operated in an inert environment in vacuum at 1,000 degrees C for a short amount of time, but it kind of points to the possibilities. There's some work that's happened with silicon carbide out of NASA Glenn that's very promising. to show us a pathway here to maximize that temperature potential. And then one of the other directions I think we could drive is instead to say, okay, we want to take electronics to a temperature beyond what silicon is capable of, but we're really going to scale on the performance. And there's some unique challenges in scaling performance of a temperature-hardened electronics. And one of those is of course, the gate dielectric. Normally, as we scale the semiconductor up to gain performance, the gate dielectric would shrink, but we inherently have an issue here because we're exposing it to a higher temperature and the lifetime has become severely limited. So we're gonna have to do something about that, whether or not that's new materials, perhaps new integration, or really choosing a new and novel transistor technology. If we're going to performance scale at temperature for mission relevant durations, there's some innovations that are required there. And so if in both of these spaces, though, we also have another challenge that's going to come up. So if we solve these hardware challenges, the next thing to ask ourselves is, can we develop relevant circuits that can operate over the full temperature range? There's not really a mission space for sticking something at a specific temperature and having it operate over long durations. And so we need self-adaptive circuits that can now go over, for instance, on scale of 1,000 degrees C. We've never attempted circuit design over such a large temperature scale, and there's some inherent challenges we'll face to realize that. And so, if you're interested in this space, especially, if you're interested in applications and in impact for high temperature electronics, or if you're really at the foundations, I'd certainly be interested in hearing from you. We've been looking in this space for quite a while, collected a lot of information, but definitely interested to hear who else would enjoy this program. Thank you.
Okay, thanks, Ben. Next up is a veteran, Dr. Tim Hancock. Tim's interests include RF electronics and digital arrays. You've heard from Tim at the ERI part of the session, but his non-ERI programs include millimeter wave GaN maturation, MGM, signal processing at RF, SPAR, and wideband adaptive RF protection, WARP. So, Tim.
All right, thanks, Mark. So this afternoon, I want to talk to you about efficient wideband modulated RF power. So on the left, you can sort of see a typical OV1 that we often talk about. And where we're headed in many cases is this direction toward multifunction RF hardware. And so to be able to build a multifunction aperture like this, we often want, we know how to build the receivers, we know how to build the antennas, but the transmitters are still a little bit of a challenge. The core transmitter we know how to build, but the power amplifier is a fundamentally very difficult problem if you want to be efficient, have wide bandwidth, and have linearity. Oftentimes we get two of those in any given design, but achieving all three is very difficult. And so on the right, it sort of gives you some examples of that. So in the area of radar, for example, we want very high power oftentimes because we're overcoming an R to the fourth propagation problem. And so we often use saturated amplifiers. Similar for electronic warfare, we may also want high power, but sometimes we also want bandwidth there. And we can usually achieve both efficiency and bandwidth, but using a saturated type of design in our amplifiers. But of course, as soon as we want linearity, we want to use that amplifier for communications, and we need to back it off. Maybe we want to use a higher order modulation. We can no longer run that amplifier saturated. And so what we often end up doing is we back off the amplifiers. Those typically look like sometimes distributed amplifiers if they're very wide band. And we get the linearity, but of course we do so by sacrificing efficiency. Now, sometimes we justify that because the communication application is maybe lower power, maybe there's other things in the system that consume more power, but it's something we simply often live with. And then the third area is sort of this overlap between efficiency and linearity. We have techniques as well to be able to achieve both of those, and they're typically things like Doherty-style amplifiers, But the problem there is those are often tuned, and so rarely do they provide a large bandwidth. They can give us the linearity at power backoff, so they're often used in communication applications, and they can be efficient. But as I mentioned, we have a problem with the bandwidth. So to sort of illustrate this, we can look at a little bit of data. So this happens to be millimeter wave amplifiers in the area of about 20 to 50 gigahertz. And this specifically shows data for silicon, but it's very similar for compound semiconductors. The numbers just move around. And so what you can see is across the top, right, at some power, you obviously are able to get very good saturated efficiency. And then as you go up in power, depending on the type of device you're using, you sort of hit the limit for that device and it will start to fall off. Now, as soon as we want to put any sort of modulation through that amplifier, what we end up typically doing is giving up more than 20 percentage points of efficiency, and we often are giving up more than 10 dB of output power. Now, that often corresponds to the peak to average ratio of the waveform that we might be running, but that giving up that much efficiency is simply a problem that we would like to be able to get away from so that we can move toward a world of multifunction apertures. And this is not a problem that's just limited to the DoD space. We see this also in commercial applications. 5G is a great example, and this is true of whether you're talking about lower frequency, sub-6 gigahertz 5G, or millimeter wave 5G. As soon as you start to get into problems where you're addressing things like carrier aggregation and the provider has multiple pieces of spectrum that they're trying to service at once, now the commercial world also ends up needing wideband amplifiers and need to be doing so with good efficiency. So what is the way that we think we can go about solving some of these problems, and what I think I'm specifically interested in? So there's two things that come to mind, and the first one is dynamic supply modulation. And so this is often some combination of envelope tracking or envelope restoration. It's often using some sort of co-design of the power supply and the power amplifier. Additionally, you can also change the bias on, say, your gate or your base of your transistor. And this can also be a slowly varying change that's just tracking average power, or this can actually be potentially tracking the envelope of the actual waveform. But the challenge with all of these dynamic supply modulation approaches is supporting gigahertz class modulation. So if you look at what is in the literature, you'll often find solutions that can support on the order of 100 to 200 megahertz of bandwidth. There may be a few hero results at about 500 megahertz. But if you want to have modulation on the order of a gigahertz or two, which is not uncommon to see in DoD applications, this approach becomes very challenging because now your power supply design or your modulator design actually becomes an RF design problem, and you really do have to start to co-design these types of things together. The other technique is, instead of changing your supply dynamically, you can also change your load dynamically. And so this is sometimes referred to as dynamic load modulation, and there's a few different types of circuits that are used to do that. I've already mentioned on the previous slide duality type amplifiers, where you have two amplifiers that work in concert to help each other. One typically works at low powers, and then the other kicks in at a higher power to sort of boost things. Similar, you can use a Schurex outphasing type of approach. That also uses two amplifiers, and they combine their power together. But in both cases, they tend to be resonant designs. Dualities use a 90-degree transmission line as an impedance inverter. They can be implemented with other approaches, but often there is some bandwidth limiting device there. Schurex is similar in that as you start to outphase the two amplifiers by more than some nominal amount, you start to build up reactive energy at the combining node, and that often has to be resonated out through your matching network. And so that becomes a challenge to be able to support a large bandwidth. And so what I would challenge the community to think about is, how do we push to these gigahertz class modulations? How do we push to greater than octave bandwidths? When you think of things like quarter wavelength lines, we often are able to achieve 20, 30% without a lot of work. Pushing to an octave is obviously about 66%. Pushing beyond that is a real challenge. But of course, 3 to 1 is well in alignment with many of our applications. 2 to 6 gigahertz, 6 to 18 gigahertz, and even in the MIDAS program, 18 to 50 is just shy of 3 to 1. And so how do we go about achieving these bandwidths, but giving up no more than, say, 10 percentage points of efficiency? So if my amplifier is nominally a 40% efficient amplifier when saturated, then you really don't want to give up more and fall back to no more or no less than 30% efficiency. But while doing something like achieving a 10 dB power backoff, so that we can run these more complicated higher modulation waveforms. And so with that, I think this is an area that I'm interested in over the next several months. Please feel free to come talk to me over the next 3 or 4 months. I'd be happy to chat with you. Let me know if I've maybe forgotten something or left out an idea here. I'm definitely open to hearing everybody's ideas. Thank you.
Okay, thank you, Tim. Next up is Dr. Whitney Mason. Her interests center on focal point arrays and infrared imaging. She's got a raft of programs. I'll name them very quickly. Focal arrays for curved infrared imagers, foci. Gain enhancement by novel impact ionization, GENIE. Limits of thermal sensors, LOTS. Reconfigurable imaging, reimagine. And wafer scale infrared detectors, wired. Whitney.
Thank you. Good afternoon. I came to DARPA from what used to be called Army Night Vision Lab, and while I was there, I worked on infrared imagers that worked in ground-to-ground scenarios. And ground-to-ground scenarios are particularly challenging because you have very diverse backgrounds, very diverse targets, very diverse confusers, and then you add weather on top of that. And when you combine all of these factors together, you often find that contrast in your system goes to very close to 0, even when having just exquisite sensitivity in your sensor. So the idea that I want to talk about today is, can we augment long-wave infrared systems to create enhanced contrast in all weathers, all environments, to operate at tactical rates. And here I'm defining tactical rates as 30 hertz. So I want to talk about a commercial example just to illustrate the point. So imagine you work on a farm, and you know that some of your plants are getting sick, and you know that they are contagious and making other plants sick. And you don't know why they're getting sick, and you don't know what a contagious plant looks like, but you do know that you want to get that contagious plant out of your field before it ruins your crops. So in the upper left, you can see a picture of what a visible image might look like, and there is no clue as to what a sick plant versus a well plant might look like. Imagine if you could add spectral capability, which is shown on the bottom, an artist's rendition of what that would look like, and you can clearly distinguish sick plants from well plants. You might know that actually such a capability exists. Farmers are fielding these systems to be able to monitor and assess the health of their fields. They work beautifully during the day. They're based on standard silicon CMOS capability. They have a few fixed filters, and they work beautifully in the daytime for a fixed mission in a fixed environment. I want to talk about translating that into a DoD relevant capability, but of course the DoD has extra challenges. We have to work day-night, and as I said before, a lot of diverse targets, a lot of diverse backgrounds. And so what I'm going to show you is that I think that you can add spectral capability to enhance contrast, but that you're going to need reconfigurable hardware that can change the spectral bands appropriately and intelligent algorithms to be able to operate at tactical rates. How would we do it today? Well, certainly broadband imagery is capable of operating at tactical rates. You can see in the top left what a broadband image might look like, and much like the visible image, there is not a lot of contrast to be pulled out here to differentiate good from bad plants. You could go to the other extreme and get a hyperspectral imager. And the picture on the right shows what such an image might look like. And certainly, hyperspectral imagery is capable of creating enormous amounts of contrast. In this picture, you might say there's, in fact, too much contrast. But certainly, you can distinguish sick plants from well plants using this capability. But it is slow. In the graph in the lower right, we see time to process an image in seconds versus number of bands across the x-axis. And you can see to process 192 bands, which is not uncommon in long-wave hyperspectral imaging, it takes 16 seconds. I want you to note the fact that there's big blue columns that say pre-processing time and little red blocks that say detection time. I'm going to talk more about this in a minute. This 16 seconds is only to process the data. You also have to acquire 192 bands. And you might know that hyperspectral is a scanning capability, and so it can take seconds to acquire 192 bands. At this point, I've driven past my target, so we need to be able to speed up that time. So how do you combine the best of both worlds, the speed of a broadband infrared system and the discrimination capability of a hyperspectral system? Well, if you just look at the graph in the lower right, the answer just leaps out at me, which is to say, collect less bands, right? If you collect less bands, it takes less time to process the information, and it takes less time to acquire the information. And in fact, preliminary research says that somewhere between 4 and 16 bands will allow you to discriminate about 40,000 targets, which should be sufficient to operate in a real-world environment. On the graph in the lower left is shown probability of classification, also versus number of bands. And there's two curves shown. The blue curve is if you just chose uniformly separated bands across the 8 to 12 region. And that curve shows that you can get probability of correct classification of 90% using only 8 bands. This is for a particular target. This happens to be sarin gas. But if you choose the optimal bands, I've called that the smart selection shown in green, you can do this as quickly as 3 bands. Now, if you had a different target, the optimal bands would change for the green curve, and you might have a different probability of correct classification, needing more bands or less bands in order to achieve 90%. But the ability to then change the bands to meet each of these things would help to do this more rapidly. Now, material solids are much more forgiving, but what we have found is that if you take the exact same target and put it in different environments, then you also have to change the bands in order to get really good signal-to-clutter ratios. So I think the 3 technical challenges are these. Number 1, how do you select the optimals, the minimum and the optimal bands in order to do good discrimination of your scene? And I think a sub question is, what is the metric that determines what minimal and optimal really means? The second challenge is, how do you reconfigure your hardware adaptively to operate at 30 hertz to provide the best capability? And the third thing is, how do you develop efficient algorithms that allow you to process this hyperspectral, this multispectral imaging rapidly? From a hardware perspective, I think there's a lot of different possibilities. In the upper left is a graph showing intensity on the y-axis versus wave number on the x-axis. This is for a chalcogenide material. By changing the bias, you can change the material from crystalline to amorphous and change the absorption band gap. DARPA has developed under the Matrix program a spatial light modulator based on this technology. DARPA has been involved in a lot of other capabilities where you can change material properties by changing strain or by changing the bias. And so I think that there are ways to reconfigure your sensor. The challenges will be making sure that you maintain light collection efficiency, that you have sufficient flexibility, but also reliability, and that you're able to do this at speed. And by the way, I don't think that you're changing wave bands at 30 hertz rates. I think that you're adapting to the scene, much like John Davies talked about earlier. You're adapting to the dynamics of what is happening, and that's going to be at a slower rate. As far as selecting the bands, I think this is a place that is ripe for deep learning. You're not trying to pull out features that are necessarily physical. You're trying to get the best separation between bands and between your scene signatures in order to be able to discriminate activity. And some work has been done in the shortwave infrared showing that this is possible. The other thing that you need to do is speed up your processing time. Remember in the previous graph, I pointed out those big blue columns with your pre-processing time. Research has shown that using, again, deep learning techniques, you can improve both the quality and the speed of your pre-processing in order to get rid of, for instance, weather effects, atmospheric transmission effects, et cetera. And finally, I think the third thing is to develop algorithms that incorporate spatial information, spectral information, and then the time, right? Instead of processing scenes one frame at a time, using video in order to distinguish targets from one another to maintain that 30 hertz rate. So I think this is a multidisciplinary program. It involves a lot of moving pieces. Would love to hear the community's thoughts on this. Thank you.
Thank you, Whitney. So our last MTO PM is another veteran, Dr. Ron Polcawich, and Ron's interests have included MEMS devices and PNT. His non-ERI programs include precise, robust inertial guidance for munitions, call it the PRIME program, and short-range independent micro-robotic platforms, the SHRIMP program. Ron.
Great. Thank you. Good afternoon, everyone. So one of the interests for me lately has been in low power, low jitter gigahertz clock sources. If I take, especially looking at high-speed serial connections, high-speed ADDs, and microprocessors. And so if I look at sort of the state of the art, conventionally we're talking external quartz crystals or MEMS oscillators, generally operating in sort of the low tens of megahertz, and generally off-board, and then routing lines to your processor. Generally we're talking fairly low power and reasonable jitter at those frequencies, but then you got to scale that up with the increasing operating frequency of the chipsets. And so that comes at some expense, right? So you're going to reduce your jitter, increase your jitter in that case, increase the power consumption. The additional challenge is you have to do the clock distribution, right? And so that's notionally shown on the left-hand side of this chart with the H-tree structure. That distribution comes at some power expense as well. And so ultimately one of the questions was, how do you bring the performance and stability of bulk crystal or bulk quartz or MEMS low frequency megahertz level clock signals to the gigahertz frequency source, and what would that enable? And so in the middle there we have an integrated MEMS notional vision where you have an Intel Xenon processor. The yellow boxes highlight possibilities of having individual MEMS potential oscillators, high frequency gigahertz level oscillators to bring you a lower swap, lower jitter, and a lower parasitic solution. So that distributed clocking also cuts down on your power distribution requirements as well. And so ultimately, does this lead us to a path of facilitating the low jitter and low power requirements for both future high-speed data processors, electronic warfare, mobile IoT, as well as edge computing challenges. And so with that, we're going to do a little bit of deeper dive. And so if I look a little bit further, sort of that current low swap, sort of technology, right? So it's a PCB mounted solution, right? Again, we're talking about 38 megahertz is generally that as sort of that clock source. Again, right around tens of milliwatts. For your power consumption, about 100 femtoseconds, give or take, is generally what you're going to be able to achieve. So how do we, but when we start to scale that technology using PLLs, we're going to reduce those performance parameters in the low gigahertz. And so one of the challenges becomes how do you get that level of performance scaled up, right? And so can we take advantage of some of the recent advances in both materials and designs to take advantage of the gains we get with the high-speed electronics. And so in the middle of this chart, we have highlighted one of the prior DARPA programs over the last decade, which is the DFIS program, or the Dynamics Enabled Frequency Sources program. This is an aluminum nitride contour mode device operating notionally right around a gigahertz. And one of the highlights from here is where you start to see the advantages of taking these high frequencies, but also some of the challenges of getting both a high Q as well as the temperature stable performance at these high frequencies. Additionally, we have lots of taking advantage of the additional industry-led developments in the aluminum nitride thin film filter space. I've kind of highlighted that with the graphic on the upper right, which is from your film bulk acoustical wave, or in this case, the solidly mounted resonator structures. Again, lots of development in that aluminum nitride filter space that we can take advantage of those and some of the gains that we've started to see in both the advantages of both the material side of things with improved performance, as well as highlighting the challenges between going from the high quality factor and that trade-off with the temperature coefficient of frequency stability, and how do we compensate for that and be able to meet all of the performance metrics that one would want for a high-speed integrated clock source. Additionally, also highlighted from recent announcements from Soitec is the piezo-on insulator. So this is taking advantage of single crystal integrated on silicon and silicon compatible substrates, and a roadmap that they have identified for both lithium niobate as well as lithium tantalate substrates in both 150 and 200 millimeter wafer platforms. So again, one of the opportunity spaces here is, can you take advantage of these advances to really push solution spaces that look for integrated clock sources. The other additional highlight would be some of the industrial research in both looking at FBARs, industry as well as academic research that's looking at both FBARs and SMR-based oscillators and identifying some of the challenges with nonlinearities, as well as the Q and frequency stability numbers that I've highlighted earlier. So one of the additional aspects is really kind of pushing forward is, looking at what that high frequency oscillator trade space ultimately looks like. And so we've taken a look at the Van Beek plot from 2012 and modified it and added some data points for some of the more recent FBAR and lithium niobate work. And this is what I've highlighted here is the normalized phase noise in dBc per root hertz per milliwatt. So power normalized phase noise characteristic. And one of the characteristics you look at across the different technology opportunities here, from MEMS capacitive, MEMS piezoelectrics, LCs, and quartz, there seems to be this sort of material limit around minus 130 dBc per root hertz per milliwatt. And so one of the leading questions is, can we go beyond that material limit, right? And that looks like some sort of material limit that might offer over several orders of magnitude of frequency, from the low tens of megahertz all the way up into low tens of gigahertz. And so that's one of the leading questions is, this is a material limit? Can we break that material limit? Can we break it through materials, innovation, and or device design and processing improvements? So these are all open questions. Additionally, what are the noise mechanisms, and can we overcome these noise mechanisms to further improve that phase noise characteristic? And one of the other highlights ultimately is this, what I'll highlight here is a low parasitic integration. To take advantage of any of these oscillators, it has to be integrated with your leading edge CMOS processor in some case. For integration here, one concept that I'll throw out there would be potentially looking at MEMS chiplets, sort of heterogeneously integrated with low loss parasitic RDLs or interposer structures. That might be your initial take on it. And then what are the possibilities of looking at the long term and looking at what is the back end of line integration. And so what are the trade-offs between both low parasitic to achieve the performance parameters of interest ultimately on a 300 millimeter a fully integrated process. And so these are some of the challenges and highlights that we're looking at. And again, not necessarily dedicated straight toward MEMS solution, but other total integrated packaging solutions from a clocking source perspective. And so really interested in hearing from the community as far as what are the opportunity spaces from both the materials, the device design, the integration, as well as for the end application space and interest from there. So if you have any interest in there, I'd encourage you to reach out and reach out for a discussion. Thank you.
All right, Ron, thank you. All right, so now we get to the fun part. So those are the PMs we're having in the session. I think we have a better part of 45 minutes or so for questions and answers, which I'll be the moderator for. We've already collected a few questions, but again, once again, please use the tool to enter questions for either individuals or for just broadly for the group. And with that, let's get to the good part. So I'm going to start with, I think, Ron again. So MEMS, you talked about MEMS a fair amount in the last few minutes. MEMS has been around a good time at DARPA. DARPA has had a lot to do with MEMS development. So tell us a little bit more about how MEMS are impacting your programs, and especially I'd like to hear what's left to do that hasn't been done already.
All right, thanks for the question. I would say that where we've come from, the MEMS development opportunities that happened in DARPA, what I was first aware of when I first joined the Army Research Lab in 1999, there was lots of development and process flows, processing characteristics, and sort of basic exploration of what you could potentially do with MEMS. I think right now what we've started to see is where can we take advantage of those lessons in the past. Take advantage of the processing that exists, take advantage of the commercial devices that already exist. And so in the current programs, within the Prime program is a classical example dominated by MEMS approaches, right? So those inertial sensors, the tough challenges associated with high aspect ratio deep etching still is a challenge today. And again, for some of those really high aspect ratio challenges, I think that's something that is, it's still dominated by, I would say, the DoD interest, especially when you start to think about the balance between where tactical grade performance is and automotive and commercial grade performance. And so, are there opportunity spaces there? Possibly. But I think the other aspect of that comes down to access, right? And so how do we access the leading edge MEMS process flows that exist? A lot of those, in many cases, and I'll throw out the sort of the FBAR SMR community, right? They're captive fabs, and so that's something that's very difficult for the broader DoD to potentially access, especially if it's dominated by our small number of parts that we would utilize versus the high volume commercial sector, which is driving that. So that's some of the interesting challenge spaces currently.
Good. All right, thank you. Whitney, I'm going to go with you next. So your interests are in the infrared world, but a lot of the work you actually do, I happen to know, ends up being electronics-based, optical electronics. So how has advanced CMOS nodes impacted some of your programs? And tell us a little bit about how, in the future, that's likely to develop.
Okay, so in all imaging, but particularly right now in infrared imaging, everybody wants smaller pixels. And before we started using advanced nodes, we were letting the node drive the capability of the sensor. And when we had big pixels, it wasn't really a problem. But as you try to move to smaller pixels, people don't want to give up things. They don't want to give up performance. They don't want to give up dynamic range. And as you know, some of my programs are trying to cram in more capability, math, other functions. And so the ability to go to advanced nodes and be able to leverage the capability to put more functionality in a pixel, I think is just spectacular for the imaging world. I'll go further. In the Reimagine program, we're actually stacking wafers. And so we're able to stack mixed nodes. We're stacking a wafer that was designed and taped out at GlobalFoundries 14 nanometer with another node that was taped out in 130 nanometer at another foundry. And so we're able to go to the right node for the right performance, and I believe that all advanced focal point arrays in the future are going to go to that paradigm where they choose different nodes and stack them together to enable the highest performance.
Different nodes or the latest nodes, or both?
I think that you choose the node based on what you need. You know, for some imaging applications, you'd really like to stay in the analog, right, at sort of big nodes where you can maximize your dynamic range. And then other places, you're going to want to go to the very advanced nodes to get that capability to put a bunch of math and things like that in the pixel. So I think that you pick the right node, not necessarily the most advanced.
Good. Okay. Let's look at this side of the room. Dave, we'll pick on you, I guess. We just had a question about CMOS and latest node CMOS. And that's the first thing, particularly in an ERI context, that's the first thing that comes to mind in most people's mind when you think about electronics. But a lot of what you do is sort of non-traditional, or at least it's not silicon. So tell us what developments are interesting in the world outside of silicon CMOS that we should be paying attention to.
Well, one example that was talked about earlier was in the M-Cubic program, the magnetic miniaturized and monolithic integrated circuits program. So these are developing spin wave devices for protection for RF systems. So we're developing on-chip self-biasing circulators that are integrable on wafer. We're developing frequency selective limiters, auto-tune filters. All of these provide protection for the kind of 5G communications devices that we're talking about now. So, in fact, they're represented in the exhibit hall by a couple of posters. One on auto-tune filters for RF applications, and the other on a compact modeling capability to put the modeling of these magnetic devices into the hands of the engineers so that they can start to integrate that into their circuits. So that's an example of a non-CMOS, but very important technology for.
Good. So it kind of actually is a nice lead into what I was going to ask Tim. So in ERI, we talk about 5G, and there's a lot of work going on in 5G. But tell us about ways in which you see MTO leveraging what's going on in 5G in a broad sense.
Sure. I think a great example of this is in the MIDAS program. Obviously, we're doing something a little different than what the commercial world is doing with the digital beamforming at this point, although I think the commercial world will move in that direction. But something that we're absolutely leveraging is the use of heterogeneous integration, complex packaging, the use of solder bumps, copper studs, 3D printing, and advanced printed circuit board design. You saw some of this yesterday in one of the MIDAS talks, where they were using an interposer to be able to integrate their CMOS, but then stack indium phosphide on top of it along with an antenna. And in that case, that antenna is made with a standard printed circuit board flow. Now, the other team on the program, Northrop Grumman, they're actually simply using TSVs and solder bumps and stacking all of the die. And most of this technology, although it's cutting edge, it's still mostly commercially available. And so they're stacking those dies, and then ultimately the antenna is built with 3D printing for that team. And that's a capability that's also commercially available. They go to a vendor to get that done. And so I think using some of these advanced packaging and heterogeneous techniques is something that we're able to leverage. We've certainly invested in it in the past, but I think it is a lot of it is starting to become more available to the community.
Okay, good. Thank you. John Davies. I want to ask you a question, kind of the same question that I got asked earlier, and see if I got it right. Anyway, the question has to do with how revolutionary and how much impact machine learning has in some of the program ideas and areas programs that you already have. How has that been a game changer, and especially in the future, how do you see things developing?
Certainly, RF machine learning really has been critical to multiple programs ongoing at DARPA that are part of my portfolio, as well as critical to new concepts. I think illustrating the role of machine learning is, I think I'll use a couple of examples from my portfolio to show the kinds of impacts that it can have and the directions it needs to go in the future. If we look at the RIFMLS program, RF Machine Learning Systems, taking the gains that have been achieved for within other domains in the commercial world, like for image processing or audio processing, and demonstrating how those capabilities can translate to RF, is a research area that had not really been fully invested by the commercial world, and by presenting some, I'll say, very unique challenges of that environment. That program has demonstrated that we can translate many of the gains achieved in audio and image processing domains, that these can translate to RF problems. And if we look at the Derby program, Digital RF Battle Space Emulator, this is really looking at a different class of problems, which is saying that for many RF applications, particularly DoD RF applications, we don't have the kind of training data that we need to really apply modern machine learning techniques. So this is an opportunity for DARPA to invest in an enabling capability that will allow the community to continue and advance and apply RF machine learning in a lot of problems that we're going to face in the future. And I'll think what I'll say broadly that's very exciting about both these capabilities is that, particularly with RIFMLS, is we've had the opportunity to take a research area that prior to the program was underserved and not the focus of commercial development, achieve some successes, and then fold that information back into the larger community and be the nucleus of further research for both commercial and DoD applications that may not have existed prior.
Thanks. Ben, a question for you. What is the major impact for high temperature electronics?
Yeah, that's a great question. It's a question we've been marching around in the space trying to find the right pull point for it. And I think we're still kind of open-ended on it, and I think there's some good application space in hypersonic vehicles and turbine engines, and that's pretty clear. I mean, even this morning we heard that from Dr. Kennedy, but there's synergy with our EW platforms. Control electronics that are needed has been communicated to us, and the amount or the performance differences between those are very much synergistic. And so really it's a compilation of communities I think can come together and leverage from high temperature electronics and really drive the volume to make it something that's actually viable at the end of the day. So I don't think there's necessarily just one application. I think there's actually quite a few applications, and really it's a matter of us figuring out what the final driver is, I think, to drive the program forward, and then we'll see the technology space be leveraged in multiple applications.
John, question for you. And you should enjoy this one. What is new in quantum for MTO?
Well, as I was just saying in my earlier little briefing, I'm really excited about these so-called Rydberg sensors. So I would, anyone that's asking about this should probably start doing their homework right away and trying to figure out how these Rydberg sensors can make a quantum sensor that could really challenge classical antennas and apertures for receiving capability. So we're marching along, and I'm pretty excited to see where that line of thinking goes.
Stay tuned. All right. So a question actually for both Ron and Whitney, but I'll go with Ron first because yours started earlier. We talked a lot about MUIs, Microsystems Explorations, and both of you started MUIs in the last few months. And I thought it would be good if you could tell us a little bit about your experience, what you've learned, just how you've reacted to those two efforts, really.
Sure. Yeah, so my MUI is the tunable ferroelectric nitrides, or TUFN program, and we basically premised that off of a research article that came out, showed ferroelectricity in aluminum scandium nitride, and lots of open questions of how real this was, how reproducible it was. But those results were so impressive that they really potentially opened up a new opportunity space for ferroelectric nonvolatile memory, especially if you consider edge computing aspects. So the MUI program was really kind of to take advantage of that and really explore those unknowns, right, from both a material processing perspective, electrical characterization, really flush out that what is real from that material set and some of those new data. A lot of lessons learned in sort of the process with just the contracting process, the submission process. A lot of headaches that we kind of crossed over since I think we were third in line with that the MUI process. But overall, we've been quite impressed with the results to date. The performers are really pushing hard from that new material, despite the COVID shutdowns earlier this spring. So I think that all in all, we've been quite happy with the progress and the overall capabilities that program has allowed us to explore.
Good, thanks. Whitney, go ahead.
Well, I suppose I should start by thanking Ron because for me, the contracting process was seamless. And it's one of the neat things about the MUI process is that from announcement to contract is 90 days. And particularly when you're a short timer as a PM, you can actually see a program go through. One of the things that I didn't know is because you do have prescribed milestones, you do have prescribed costs, how much diversity were we going to get in the proposals? And so I have the GENIE program, and we have funded 5 completely different solutions to meeting 2-micron cutoff room temperature or high operating temperature linear mode APDs. And it really expands the space of what is possible, and I'm hoping that some really neat things will come out of it. I hope we do more MUIs in the office.
Good. So I think I'm going to ask a few questions which are more or less open to the group, so jump in as you want. So let's start with this one. Tell us a little bit about your interactions each of you have with the user community. Do you deal with the defense community, with the commercial community? And how do you find the balance between those two? Particularly as regards some may be more interested in near-term results and some maybe not so much, looking for more disruptive things.
Okay, I'll go. Most of my interactions are with the defense community. Infrared imaging really is extraordinarily useful for the military, not really so useful for commercial activities. And so most of my interactions have been with the Defense Department. And I've been really lucky because, as you pointed out earlier, a lot of our stuff ends at TRL 5. Which is not ready to go strapped onto a plane or ready to go, on the head of a soldier. And so I've engaged a lot with military labs, with DoD labs, with other agency labs to start the conversation, right? So in one of the programs that I have, the core of my program actually provide support to who I think the ultimate customer is, and that's how you balance between having a TRL 5 system at the end of your program when the user really wants you to be at TRL 9.
I'll throw out that engaging with the end user community is critical in really finding the most impactful problems. That we have to prioritize our research to make ultimately the biggest splash in that end user community and tackle the problems that they often cannot directly solve themselves. And and I think that is fundamental to any program project that we work here. To continue the thread of transition, I mean, ultimately, we're not here to build shelfware either. We know that we're going to create something again at a TRL less than 9, and having that buy-in from the end user community that the capability that we build will actually be useful to them and that they are committed to taking it the rest of the way, I think is an absolutely critical element to any successful program.
If I could follow up, especially with the end user aspect of that. So most of the stuff that I've been working on is mostly DoD engagements, and I think that user input, especially from both, as Whitney was saying, from the DoD labs to do the testing, or even the field evaluation kind of engagements, right? That's going to help facilitate that crossing that tier level 5 gap. And so we've started to see that within the prime program, getting that early engagement, getting them maintaining that engagement through, and obviously looking for those field evaluation opportunities next year. So absolutely kind of, I think that's sort of been critically advantageous for us within that program.
So I also happen to mostly engage with the DoD community, but I think one of the things that I found that it's almost a critical job of a program manager is, you see us talking to performers, we meet with faculty members, we meet with defense contractors, and we're hearing about your great technology, and sometimes we're hearing about defense problems, but mostly about your technology. Then we often have to, we talk to those end users, and we have to sort of critically understand their problem, because it's not uncommon that an end user will bring you a problem and it will turn out it's not actually the real problem, right? That they are bringing you a problem, and maybe the initial complaint is my radio doesn't work the way I want, right? But then you have to actually dig deeper and figure out what's not working. Why is it not working, right? Is it a problem with the hardware? Is it an MTO problem, right? Because oftentimes it may be some other reason that they're having an issue. And so often program managers, I think, end up being matchmakers in that we have to be able to talk to that end user community and understand their problems and interpret what potential solutions may be able to help them, both potentially in the near term, but usually a little bit into the future. And then do that matchmaking with where we see technology at currently and where we think technology will be heading. And I think it's that matchmaking that program managers often have to do. And when you get that just right, I think that ends up making for a really great program that often can be ripe for transition if that technology is headed in the right direction, and then that end user will be there to hopefully catch it.
Yeah, I just would say that I end up spending a lot of time with people that put boots in the sand, and there's a tremendous thirst from these folks for technical capability, especially as they go out and they see what's available in the commercial space. And so, that's one of my perspectives on ERI and why it's so critical is because the commercial space is able to drive forward and create such amazing capability out in the space, and the ways that we can go leverage that that capability for DoD applications to meet the DoD niche needs that might not be as high a volume is a really critical thing to provide these folks with the type of capabilities they're seeing in their commercial spaces.
And to echo Tim, I think the engagement with the user community is critical because in MTO we're often doing components. We're not presenting the end user with an entire system that he can use. So to have that engagement with how do we move the transition along, what kind of things can we invest in to help get to that point where it is something that the end user can use is critical.
I'll echo also what Tim said about being an interpreter. I feel like there's actually 3 communities that I somehow end up interacting with. There's the user community, boots in the sand that have a problem, and then there's sort of the research community and laboratories trying to understand where to find an impact for their technology. And then there's this third community of people that aren't connected to either one of those, other program offices, other government agencies, FFRDCs, trying to figure out what the other two groups are thinking. So you find that it's more of a Venn diagram that I feel like I'm trying to always interpret between the different groups. And that's been, I didn't realize that coming to DARPA that would be part of the job, I think, but it's been a pretty rewarding experience trying to understand how all these different groups see each other. And I think it shows more about DARPA's leadership in this sort of area, trying to figure out who needs to be talking to who.
Okay, John, well, let me pile on to that because it actually leads into my next question. So I'll add one bubble to your Venn diagram. Let's talk about universities and academia. So how important are university efforts to each of your programs, and what's that balance? How do you balance between fundamental research, and they really typically want to do things that are more in that extreme, versus something that is going to benefit those other bubbles that you talked about?
Yeah, that's a really hard problem. I feel like that the sort of standard approach is to do it in universities first and then make sure they can do it, and then kind of move up this technology readiness level step by step. To me, I try to structure programs such that as much as possible things can happen in parallel so they can go a lot faster, where you have university groups working with prime contractors, defense primes, and other government agencies, and sort of really try to make that Venn diagram happen in real time. Otherwise, yeah, you end up in a situation where you're waiting for a breakthrough to happen, and for everyone to kind of agree upon that breakthrough before you can actually move to the next step. That's the approach I've taken, at least.
Yeah, so I guess I'll comment. I think it sort of depends on the type of program that it is, right, and what type of funding is available. Oftentimes, you may not be aware, right, but we often break the problem and the funding of a program into sort of 6.1, 6.2, 6.3. And if it's a very early program, right, then I think it makes, so a 6.1 or 6.2 type program, it absolutely makes sense to sort of have this technical area that you go and you push on, and everybody sort of works together, competes, and they're trying to come up with this new breakthrough, like what John was saying. But I think there's other types of programs, and MIDAS is an example of that, and I structured it in a certain way to where I had two technical areas that focused on the chip development and the heterogeneous integration of the aperture. And I knew that I wanted these to be transitionable products, basically, at the end, right? We wanted to be able to solve these problems. And while certainly universities could contribute to it, the overall scope of that type of work was simply larger than what a university team could tackle. And it was a more mature technology with a different risk profile. And so that was obviously funded with 6.3 funds. However, within the program, there were still hard research problems related to millimeter wave, next generation apertures and digital beamforming around noise and dynamic range and things like that. And so we created this separate bucket basically for the academics, so they didn't have to compete with the defense primes, but they could be working on similar problems, but be able to focus on them just part of the problem, right? So they could go design, say, part of a single element of a phased array, or work on just the DACs or just the A to Ds. And what I found is that that's been actually very fruitful. And while there isn't a strong connection between the two from a programmatic standpoint, there's no requirement that the academic work directly feeds into the work by the defense primes. What we find is it actually is in some cases. A great example of that is some DAC work that's been done at Stanford in pushing the area of FinFETs, using them for new DAC architectures. But both of our performers are either using or looking at using FinFETs in the next phase of the program, and both of them can potentially leverage some of that DAC technology that performer has already started to publish results on that they've accomplished in phase 1. And there's several examples like that from academic performers. And so they get to describe it early at program reviews and such that the defense primes get to see it and potentially leverage it as they move forward throughout the program and solve problems that they're up against to be able to execute the subsequent phases of the program. So what I found in Midas that to be very useful, to have them sort of on this equal footing but not necessarily competing with each other, and I think it's worked out well in a case like that.
I'll throw out that a critical secondary benefit working with university performers is that we're contributing to training the next generation of DARPA performers and even DARPA personnel. I myself, many years ago, my graduate research was sponsored by a DARPA program. So I think investing in that pipeline through DARPA's university relationships is really a critical secondary benefit.
Sounds good. All right. Thank you. Let's move on and let me ask a question to the group. And I'm looking over in this side of the room especially. How will zero trust impact some of your programs? Any takers on that? They're not all easy ones.
Can you restate the question? By myself, another 20 seconds.
I'm trying to imagine what the person who asked it had in mind, but I think what they're saying is the DoD policy moving towards zero trust is going to affect our ability and change our supply lines in some respects. And will that have impacts on any of the research that you do, or not? If the answer is no, then that's fine.
I think in some cases it can. But one thing that I've seen is there is a desire to move toward a higher level of functionality in many of the chips we design, right? In the sense that they need to be able to do multiple things. They may be able to need to do different things in the field. And so programmability is sort of required and necessary from the get-go, just from a pure application standpoint. And what we found is, I think that the fact that programmability is there, it does bring some amount of trust, because similar to the way we treat microprocessors and FPGAs, that essentially, when unprogrammed, they're just dumb pieces of silicon, and there's a little bit less of a concern there. And so what we find, I think, is we're adding more and more capability and programmability and reconfigurability to even our most application-specific type of integrated circuits. And by proxy, it does buy us some level of trust. And then I think you can go to that next step, right, where you build in keys and locking mechanisms and this, that, and the other that buy you an additional level of security. And so I think it doesn't affect any of my programs immediately, but then you can sort of see that it does sometimes affect our performers in their choice of, I would even say, silicon technology. Because oftentimes if the choice is to fabricate something through a trusted flow versus a non-trusted flow, they often prefer the trusted flow, which is often good and the right answer, but sometimes it's not always required, especially while doing the research. But there's a desire to do that. And so sometimes you have to make sure that you're picking the right technology for what you're trying to do, and not just sort of get railroaded into the wrong technology because it happens to be trusted. So I think you have to balance trust at times depending on what you're trying to do. I think we're all trying to both protect what we design and follow the laws and the executive orders that are in place. And it's a complicated, sticky issue that is dynamic at this point in almost week to week, it seems.
It's a very balanced answer. Yeah. Any other takers?
Yeah, the Reimagine program actually thought about this before we started. Again, most infrared focal point arrays are ITAR protected, and the DoD has a serious concern, has always had a serious concern about sending out designs into non-trusted foundries. But just like Tim said, the bottom tier of Reimagine is a reprogrammable device. And in fact, until you program it, it's just actually standard cells taken from Global Foundry. And so there is some measure of trust there. We protect the software, we protect the programming. But we're taping that out in a non-trusted foundry. But I pointed out that we're stacking devices, and those are coming out of trusted foundries. And so, much like I said, you would pick the right node based on your device, your performance requirements. You could also pick the right node based on how much trust you needed to inject in that. And that's something that we think about actually in our programs.
So if I can add, especially from the ITAR piece of it, right? One of the things from the inertial sensor, side of things is that gap between, or that boundary between sort of tactical and navigation grade. And especially when you start to think about autonomous vehicles and where that sector is potentially going to go, improved inertial sensors would be advantageous, right? But then we have the ITAR boundary for some of the performance there, objectives that we're trying to hit for some of our other programs. And so that's an interesting space of how do you deal with that aspect of it. And again, if I boil that down to two things, very similar to what Whitney was talking about, the MEMS piece of it, silicon micro machine structures, right? It's essentially dumb the way the way Tim was kind of describing some of the silicon pieces. It's not until you put a very sophisticated ASIC with it where you get that, you can leverage that and get that performance out of it. And so that's an interesting trade space. Again, beyond DARPA, but again, from an ITAR perspective, it's something we think about.
Okay. So next question. So earlier I was recommending in the last session, the MTO 101 session, that people interested in ideas and DARPA funding and so forth come contact you all, program managers, and spend time with you giving ideas and so forth. So the question I would ask of you is, what's the number one thing that you wish people knew and understood before they came to talk to you to sort of help them when they come do that?
Yeah, so we were actually talking about this a little bit earlier today after some of the conversations we had last night. And I think, and Mark, you talked about it in the 101, I think the number one thing that folks need to realize is that if you're coming to us and you have a new technology and you really want to tell us about that technology, but it's not in our interest area, you don't know that we're already thinking about a program in that space, then we have a hard time necessarily connecting that immediately unless it's really in our background. And so if you instead come to us and say, hey, here's how what I'm going to do is going to change the world, it's going to create new mission space for the DoD, for the warfighter, tell us that first, because that sets the hook. That lets me know it's important. And then second, come tell me what's the problem you're going to solve. Not the problem in the DoD, but what's the problem with technology that you're going to solve that's going to enable you to solve a DoD problem. And then the third thing is, tell me what are the technical challenges that you see that you face today to be able to solve that problem. And if you can accomplish some, not to perfection, but some level of that, it really sets the backbone for me thinking about it as a program, and not just you showing up and showing me a capability and telling me that you solved the problem. Because if you've solved the problem, it doesn't give me a chance to invest in it, because DARPA is about solving problems, about taking technical risk. If you've already accomplished what you set out to, then there's other avenues in the government that can go fund that going forward. And so that's the best way. At the end of the day, like Tim said, we're here to help you make those connections between DoD applications and your technology. But if you can start to lay out some of that framework, it really makes it easy on the program manager to create a new program in an area that you probably want to apply to.
Yeah, so I guess I'll echo some of what Ben just said. It all comes back to sort of the Heilmeier catechism and being able to answer those questions. One of my biggest pet peeves is when somebody comes in and they sit down with me, or used to sit down with me, and they spend a half an hour telling me about all of the great things that they've done, right? They tell me about their research group, they tell me about the papers that they published, and they show me 50 slides. But I would much rather hear about the thing that you had trouble solving, the one that you didn't actually solve and publish the paper on yet, right? I want to hear about your problem and maybe your potential solution to solve it. But don't come in just telling me about all of the problems that you've solved in the past. Obviously, some of that is useful, right? You need to let us know that you do good work and sort of what area that you work in. But being able to outline a problem and show that there's a path to potentially solving it, I think is key. I think the other thing that people should know is, don't take rejection personally, right? This is, I think, hard even in the beginning as a program manager, that it's hard to say no, and it's hard to give that sort of negative feedback. And I would say some of the times the negative feedback is not because it's maybe not a good idea or it's not interesting technology. It may just not be sort of applicable to a DoD problem, or it may not be applicable to something I'm interested in right now, or maybe it's not well aligned with MTO's strategy, right? I've had people come to me with interesting technology, and I'm personally interested in it, but then I sometimes have to take a step back and say, okay, well, that's interesting, from a technology standpoint. However, it's sort of not aligned with what we need to get accomplished right at the moment. And so that's not necessarily, it doesn't necessarily reflect, poorly on your idea or even the problem. It may just not be well aligned, and you may just need to find a different program manager or a different office in the building. And so people should not take, rejection personally. I think that's just one of the sort of the side effects of this business, I think. So
I'll just pick up on that again and re-emphasize the Heilmeier catechism. The more you can come to us with those questions well answered, you're going to make our lives a lot easier, including the why now question, which is what you were just talking about, Tim. That's not about the problem. It's about why we should do this right at this moment. But again, we're going to have to answer those questions, so you might as well give us some good solid inputs before we can really engage.
I'll add one more thing, and I think it's really critical to familiarize yourself with the programs that are already ongoing at DARPA. A lot of this information available on the DARPA webpage, but it's not enough just to define a problem that needs to be solved. You need to make sure that it's a problem that isn't already being actively researched in a particular area.
Okay, good. All right. I think this might be the last question that I'll get to ask, but I wanted to end with a good one. And it's along the same lines of what we were talking about, people who come visit you and pitch ideas to you. Can anyone describe maybe the strangest idea that was presented to you, hopefully that you later discovered or decided could be a good idea?
I'm not sure if I have the good idea one off the top of my head, but the strangest was there certainly was a time machine that was proposed at one point. There was also the person whose technical accomplishments related to cotton candy. That was also interesting. Most of the technical ideas I've gotten haven't been completely off the wall if they're well founded, but we do get some interesting concepts that come in the door.
Being in the quantum information sciences field, I get some doozies. I'm not going to go through all of them, but harvesting energy out of the quantum vacuum and basically making a perpetual motion machine, I've seen a few variations on that theme. One good idea I got rather recently, not quantum at all, it's using lasers to as basically an acoustic receptor. That ideas, like I hadn't thought of that, and someone brought it to me, and it was such a good idea. We moved on it very quickly, and so it kind of goes to show you how fast a good idea. I think that was, I don't know, 4 or 5 months from first phone call to money out the door, ready to do work, which is, I think, pretty fast. So you can come, we can do good things quickly if it's a good idea and you've done your homework.
Okay, unless there's more, we have time for one more question. I'll ask another one. We have PMs ranging from seniority of just a few months to many years, quite a few years. I think, Tim, you're what have you enjoyed, particularly for you guys who have been here longer? What have you enjoyed most about being a DARPA PM?
I'll actually relay what Bill Chappell told me when he was recruiting me, and it's imagine having the entire United States working for you, right, to solve the problem that you want to go solve, and that's a pretty powerful thing when you think about it. To be able to, I'll come back to Midas, right? I have 2 really great teams that are made up of defense primes and commercial industry. I have 10 performers in the sort of academic bucket that basically span all the best universities in the country and a small business. And that's a powerful thing to be able to solve a problem. The other thing that's really great about it, in contrast to, I would say, sort of things I've had to do in the past where you're sort of a line manager and you're having to manage people and projects, often in that role, you're sometimes looking at the Venn diagram of what can I get accomplished technically, and do I have the right people to go do it, right? But as a DARPA program manager, that second boundary condition goes out the window because there's somebody out there that can technically do it, right? And they're going to respond to your BAA and they're going to propose an idea. And so you really just need to define the problem well and put some solid metrics behind it, and you will have the best people in the world working on that problem. And that's something that I think you have a hard time doing almost anywhere else other than DARPA. And so I think that's been a really exciting piece of the job.
The access to talent has really been amazing. You put out an RFI and people come out of the woodwork with stellar qualifications, great ideas. So the fact that people answer my emails and my phone calls is refreshing.
I'd say the best part of this experience so far is just direct interacting with the warfighter, going shoulder to shoulder on some things that's pretty interesting. And getting to talk to folks, like there's a gentleman in the building who's flown 6 aircraft in combat, different aircraft, and that's amazing to get to talk to those people and leverage their experiences and hear what their problems were and see how the things that we're doing today could impact them of the future.
I'll chime in that I think for me it's the learning experience of, from the academic point of view, you can call up someone that's not necessarily right in your field and they'll take the time to explain to you something and you can learn a lot. That's been very valuable. The other program managers, they all are amazing people and will take the time to tell you something about their field. The liaisons, the boots on the ground, and we get to have some fun experiences at DARPA. I got to ride an F-16 once. That was pretty awesome. And I actually learned a lot. It wasn't just a joyride. Going to visit submarines, a submarine captain, and learning a lot about submarines. Like these experiences you would never have, I think, working. Not necessarily never. I don't want to use absolutes, but hard to have that set of experiences all in a short amount of time. It's been very great to see all and learn from all these folks.
Okay. Was there anyone else? I think let's call that a wrap. I want to thank all of you, all 7 of you, for your thoughts, for being here, and enjoyed it. And I hope it was useful to our audience. Thanks again.